Hi, welcome to problem session 4 of EE292P. Today I'm gonna talk about inductive boost converter. We'll continue the same example from the previous session. So first we'll start with steady state operation, and specifically we'll calculate DC gain, duty cycle, and efficiency of the converter. Then we'll calculate current ripple for the inductor to find the boundary between continuous conduction mode and discontinuous conduction mode. Then in the second part of this session, we will analyze the frequency response of the boost converter. We'll start with the open loop transfer function, and with that, we try to design a compensator for a stable closed loop operation. So the converter that we're gonna discuss today is a boost converter that's designed for LCD backlighting. So in this case, the input is a 4-volt that comes from single cell lithium ion battery. And then the output is 6 strings of white LED drivers. So this is a normal case in LCDs that's used for monitor displays or laptop displays. And then in each string we have 10 LEDs in series. So now we know that the forward voltage for each LED is 2 volt. So this means that each string needs 20 volt for all LEDs to turn on. And then for full brightness of each LED, we need to provide them with 20 milliamp of DC current. So it means the total current that needs to be provided by this boost converter is 120 milliamp. The passive components in this circuit are, so the capacitor is 4.7 microfarad, the inductor is 10 microhenry, and the converter switches at 1 megahertz. So here's an example of a boost converter by Texas Instrument that is suitable for this application for LCD backlighting. But we can work with a simplified block diagram, and here is a simplified version. This is our input source, 4 volt from battery, 10 microhenry inductor. We have a MOSFET switch that's on for duty cycle part of the switching frequency or switching period, and then there is a Schottky diode, and this conducts during off time. We have the output load capacitance, and then the load, which is 120 milliamp drawn from a 20 volt. So before going through the different part of this example, let's quickly review our naming convention for our example. So I use a lowercase il of t to show the time domain inductor current in this case. This can be applied to any other voltages and currents in my circuit. Capital IL denotes the DC component of the inductor. Lowercase, we use that for a small signal. And then when we have S in parentheses, this means the AC component in Laplace domain. Delta is used to denote peak-to-peak ripple of the time domain signal. So basically this parameter is the difference between maximum and minimum of the time domain signal. We use low ripple approximation to simplify our calculation throughout this example, which basically means that our peak-to-peak ripple is much lower than the average value of the same component, in this case inductor current. And also we use the averaging over one switching cycle in both first part and second part, and we use this notation for that. And under a steady state assumption, this average over one switching cycle is basically the same as DC component. So now with that, let's move to the first part of the problem. So in the first part, we want to calculate the DC gain of the boost converter as a function of duty cycle. If we use inductor volt-second balance, under ideal condition, we know that this gain is 1 over 1 minus D. We calculated that in our previous session, and Also using capacitor charge balance, we see that the average of the inductor current is basically 1 minus d times the load current. So basically in a boost converter, the input voltage is boosted by this higher than 1 gain ratio, whereas the input current or inductor current is bucked or attenuated by the same ratio. So if we plot this voltage gain 1 over 1 minus d as a function of duty cycle, we will get this nonlinearly increasing behavior. And as our duty cycle approaches 100% or 1, this gain goes to infinity. Of course, there are practical limits in this region which limits our voltage gain. We will see them later. Now our goal is recalculate this DC gain relationship between the output voltage and input voltage when we have lossy components. So specifically, we add a series resistance to the inductor, and also we assume some RDS on or conduction resistance for the MOSFET device when it turns on. Also, we assume that our diode is non-ideal, meaning that there is a forward voltage whenever it conducts. So we need to rewrite the inductor voltage and capacitor current equation, and then do volt-second balance and capacitor charge balance to calculate the relationship between VO and VI. So let's start with on state, when the switch is on and the diode is off. In this case, the voltage applied to inductor is the difference between VI, the input, and the voltage drop on these two resistors, which is the, assuming again low ripple of the inductor, we can assume that the current going through these two resistors are constant and are the same as the inductor current. So we can say that the voltage applied to inductor is VI minus IL, the inductor current, times total resistance. And again, assuming low ripple, this time domain signal is constant during this period because all of these variables are constant. For capacitor current, it's very simple. Whatever load current we have, it's drawing from the capacitor. So capacitor current is basically an inverted version of the load current. During off state, the diode conducts, and we model that with the forward voltage of VD. So the main switch NMOS is off. So in this case, the voltage applied to inductor is input voltage applied to the positive terminal minus the voltage on negative terminal, which is the output voltage, plus VD, plus the voltage drop across this series resistance, which means VI minus IL times RL minus VD minus Vout. And then in this case, the current to capacitor is the difference between the current that's coming in from the inductor and the current that's drawn by load, which means IL minus I load. So now we can write a capacitor charge balance equation. So the average of the capacitor current over one switching cycle should be 0. This means D times the capacitor current over the first part plus D prime, or 1 minus D times the capacitor current during off state should be 0. And this means the inductor current should be the load current divided by D prime. This is similar to the ideal case. So if we include losses, there is still this relationship between input current and load current. Now, how about the relationship between voltages? So we write inductor volt-second balance, and again D times the voltage applied to inductor during on state plus D prime times the voltage applied during off state should be 0. And if we rewrite this equation, we will get this equation for V out over Vi, which is basically 1 over d prime, and remember this is the ideal gain, times this parasitic term that comes from lossy components, which is the diode contribution, d prime times V diode over Vi, and then the resistance contribution, which is the load current times ESR of the inductor plus the on resistance of the switch divided by the input voltage, and these are weighted by duty cycle and d prime. So now in our previous plot, I add the non-ideal case. So the blue waveform here shows 1 over 1 minus d, the ideal gain, and the red waveform shows a lossy case. As you can see, for any given point of duty cycle, the red shows a lower point, and this is in agreement with our intuition. Because of loss components, we get less gain or less output voltage at a given point in duty cycle. And this is more clear at the very high duty cycle because our loss terms become very big, and this limits our maximum voltage gain to somewhere around 6.5. Specifically, we are interested in the point that our gain crosses value of 5, where the input voltage of 4 volt will give us 20 volt output. This is what we need for our application. So in the case of ideal converter, that happens at 80% duty cycle, as you can see here. But for the lossy component, we have two crossing with the horizontal line with value of 5, and the lower one, which means the minimum duty cycle that can give us a gain of 5, is around 83.8%. So it means that I have to increase my duty cycle by about 3.8% to get the same gain value. So with this duty cycle, we can calculate the efficiency of the converter. So we know that the efficiency is the relationship between P out, the ratio of P out over P in, the output power to the input power, and that can be written as the output voltage times the load current divided by the input voltage times the average of input current. Using the low ripple approximation, we can say that this average is same as the average of the inductor current. We know that the ratio of output voltage to input voltage is M of D, and then the ratio of load current to inductor current is known from capacitor charge balance equation, and that's 1 minus D. For duty cycle that we just calculated, 83.81%, we can plug in the numbers, and turns out that the efficiency in this case is 81%. So we lost 20% of our input power due to our lossy inductor, on resistance of our MOSFET, and the diode with non-zero forward voltage.